Hallo, wie geht's? No, I'm just kidding. I'm from Cape Town. Um, by a show of hands, who here has written a single line of code in their career? All right, and who's a day-to-day developer? They would call themselves a developer. All right, cool. Just getting an idea. Today I'm going to chat about modern blockchain indexing and what that looks like. So I'm going to start with just this teaser slide, and we'll come back to it, we'll unpack a little bit more. But it's just to kind of highlight that when I talk about modern indexing, we're working in a space where there's a lot more data than it used to be when blockchains started. And in order to index all this data, we need to apply some Web 2 technologies into the Web 3 space to really make this faster. But I'll come back to the slide. I'll touch on it a little bit more. First, a little bit about myself. My name's Denham, like the jeans. I'm the co-founder of NVO. I'm a believer in the tech and not the hype. My academic background's in computer science and economics. I'm an anarchist at heart. I can see the emojis have got a bit wonk. And I've been developing in the space since mainnet gas prices weren't so high. A little bit more about myself and the ecosystem. I'm a Puli holder, recently a Grounds DAO member, very cool DAO, if you want to check it out. It's a Nouns DAO fork about coffee. And I think most notably, I'm a safe guardian. Cool. By builders, for builders. Now, this is going to be maybe a little bit of a brag, but I just want to maybe add some credibility to who I am and the team I work with. But we are big builders at heart. We've attended several hackathons around the world, noted the first one in Cape Town, going to Denver, Bangalore, amongst a couple others. We've been fortunate enough to present at events in Davos, New York, Barcelona, amongst a few others too. And some of the smart contracts we've architectured have securely, for several years, held over $75 million in value. Excuse that slight brag. All right, so my talk on modern blockchain indexing begins with a story. So there were three little builders founding a Chad DeFi startup, and after a year in production, their data indexing would take a week to deploy. At the time, we were using subgraphs, and it was quite harrowing, or it was quite scary to think that if our indexer went down and we had to start it from fresh, it would take a week for our kind of back-end system to present data to the front end for it to deploy, which is quite a long time. And this is quite scary in the concept of going down, and we actually got a grant from the graph to build like a more robust version. It was called Subgraph and Crashable. And eventually we decided to take the leap and start building an indexer for ourselves. All right? And this indexer for ourselves, we felt was materially better. And so what we started to do was generalize it so that other applications can use it. Cool. Coming back to this slide, and we can unpack it for a little bit. This is the amount of time it takes to index a single Uniswap pool, and keep in mind there are thousands and thousands of Uniswap pools running benchmarks across a few different indexes. You can see with the graph on the one end, subgraphs, it's just under 17 hours, and with us, it's just under 10 minutes. So that's quite a noticeable jump. And what that practically looks like in the context of float, that's about 104x speed improvement. And so it took our 1 week deployment time into 1.6 hours, which is quite substantial and allows for a much faster iteration cycle. Just think about when a product team comes to you and says, cool, we want this feature, and it's like, cool, I started working on it, it's done, it takes a week to deploy, and then say, okay, let's change it up a little bit. And you got to redeploy it, and then you have to tell them, oh, it's going to take another week. And this is quite a narrow example in like a defined case where it was about a week. But for example, the Uniswap indexer takes about V2, takes about 40 days to deploy. So that's quite a substantial difference. All right, build bigger, ship faster. We have some of these stickers around, but I just use that to kind of break the flow. So at this point, we've chatted about why we needed it. and we've touched on how much faster it is, but I think if we want to chat about modern blockchain indexing, we should dive into how we actually do it and what that difference looks like. So let's jump back a little bit. Let's take a look at how you get blockchain data. All right. So you get blockchain data from a node, and you usually make an RPC request, a remote procedure call. But essentially, you say, "Cool, node. This is the function I want to call. Fetch that data for me and send it back." And you can see in this diagram we've got the client and the blockchain node, and we've got two kind of example RPC requests there. I think it's meant to be get block and not get block data, and the second one is get logs. But essentially what's happening is you send a request, you tell the node what data you want to get, and it sends it back to the client. Now, this has two major bottlenecks. So we identified two major bottlenecks in this kind of process. And sorry, one other thing I just want to chat about as well. Maybe I'll get to it. Okay, so the two challenges were network and bandwidth, i.e., you're sending data over RPC, and it's a lot of data you're collecting, so it's innately slow. You're limited by your internet speed. The second thing, which is a little bit more vague and open, is application design. So a blockchain node is designed for consensus. It's designed for kind of adding new blocks to the chain. It's not designed for getting data. However, it can be used for getting data. It isn't designed specifically to be performant in getting data. Now, something like get logs is a method you use to get event data when people interact with smart contracts, and that can build up over time. You can get quite a lot of events, so it can be quite a lot of data to transfer over. And so we identified this kind of challenge. Sorry, just to give you maybe a very, very crude example of what this could look like, and don't shoot me, but essentially imagine you have 3 gigabytes of data you want to collect, and you're storing it in a text file versus a database. It's obviously going to be faster to fetch from a database. Now, that's very crude, but I just use it for illustrative purposes to touch on that nodes aren't designed for getting data. So pretty straightforward. We developed Hypersync. And Hypersync, in the simplest terms, is a node designed for reading data. All right? So it's designed for querying really fast. We say mega fast, mega flexible, and real time, which is awesome. And what we did to kind of change things up, and a little bit more of the technical behind the scenes, we developed this node so it doesn't perform consensus. It's more of just a data lake, so it won't keep your blockchain alive, but it will be, it's kind of focused on getting data. And we really just applied a lot of Web 2 technologies to the Web 3 space. So we took modern database technologies and applied it into the Web 3 space. So here's kind of a simple example of something we implemented, which is called Parquet. And the way we store the data, so you might be familiar with kind of row-based records. We all store data in rows. And this, we shift it, and we store it in columns. Seems pretty simple. But interestingly enough, you're reading this data from disk. And so to search through disk, it's a lot faster if the indexes are next to each other rather than in a row-based format. Super simple, but really has some kind of notable improvements on how you get that data. The alternative would be if you could get everything into RAM, but if you look at something like Arbitrum, which is 7 terabytes for a full archive node, you obviously can't store 7 terabytes in RAM. So you've got to start optimizing for disk reading. Cool. Another thing, any Rust stations out there? Any developers in Rust? It's an extremely high-performant language that does some clever things with memory, and we built the system in this. This diagram I'm showing you here is actually just the comparisons between different clients, different nodes, and you can see how much Reth, which is a Paradigm recent implementation, is quite streaks ahead. You can see time to sync 50 hours versus the next app, which is 5 days, and Geth and Nethermind getting to 1 month. So quite a jump in performance. Another bit of the secret sauce, just to touch on Hypersync, is we implemented something called I/O Uring. I won't dive into it too much, but with a package called Glomio, a Rust crate, we were able to optimize read and writes to disk. So again, some super powerful technology, but completely available and accessible, and it allowed us to increase the read and write speed to disk. Cool. So a lot of people think of indexing as similar to subgraphs, where you have an application, you've got events coming out of your contract, and you want to understand how your users interact with, and you aggregate that data. Now that, in this context, is hyperindex. And hypersync, what I've been chatting about now, is a kind of full representation of the blockchain. And so it's much more raw data, but it's the engine that plugs into hyperindex and allows us to index extremely fast. So that diagram I was showing you earlier, that was indexing specific events from a contract, from a Uniswap swap pool, and that's on hyperindex. And beneath the hood is this engine hypersync, and that's what we use to facilitate it to be so fast and be a lot more developer friendly. I also want to just give a special mention to HyperRPC. So HyperSync is our own custom API, and it's because RPC is unfortunately bottlenecked by network and bandwidth. And so what we did to make it a little bit more plug and play, a little more friendly to people trying to access data, is we put a RPC layer or kind of conversion on top of HyperSync, and so you can make normal RPC queries, and that'll automatically get converted into HyperSync queries behind the scenes. It works really nicely for plug and play, but unfortunately, again, it's still sending the data over RPC, and hence a little bit, we don't really get the speed optimizations from network and bandwidth. However, you can still search massive data sets and get the queries you're trying to get a lot faster. Cool. So definitely follow my co-founder, John. He's done some really fantastic examples of hypersync in action, specifically like aggregating or making queries into getting raw data, particularly good for analytics, other kind of applications you want to look into. And here he's got two examples. The one is in under 15 minutes, he was able to get 89 million transfer events on ETH mainnet for USDC. That's pretty impressive that within a kind of single query, you can wait a little bit and you'll have this response. The other example there is something I think super cool, is he's essentially passed in an address and got all the transfers and related to that address, and that's in 0.67 seconds. Now, with speed like that, you could build a block explorer with no backend. You simply get the data directly from the raw data directly from the chain, or hypersync in this instance. So really cool to see these. He's got 30 examples of this coming out, and they're coming out day to day, which is pretty cool. Definitely recommend checking it out. And then, yeah, we have kind of gone to market quite recently. We're quite a nascent product. We are getting a lot of really fantastic feedback, which has been pretty exciting. I think if you kind of read into this, it's like crazy how unbelievably fast your product is. It really just highlights that the feedback we've been getting is around speed, and it's been pretty motivating. It's been very exciting. And then wrapping up, we've got docs, everything in nvo.dev. You can check it out. The link to Discord, Twitter, etc. will be there. However, that's our Twitter handle, nvo indexer, and it's also our YouTube handle. There's some really great speed runs, kind of 2 minutes to break down everything. And then that's my Twitter handle below, Denham Preen. Cool. Thanks, everyone.
Thank you.
Are there any questions?
Yeah, we have time for a few questions, so don't leave the stage yet.
Cool.
Yeah, does anyone want to start? Here's a question. Thank you, Cliff. Just 1 second.
Thank you. Great presentation.
Thank you.
I was just wondering about some details. You were talking about indexing events on Uniswap version 3 pools, but it's kind of vague. If you simply retrieve and are able to basically query all the swap events, it's not that interesting. But can you reconstruct the internal state of the given pool from the events in that same amount of time? Like active ticks and where the liquidity is located, stuff like that.
I mean, so the hyperindex layer is you can kind of absorb the events, and you can do what you want with those events.
I see.
And you can aggregate that into the...
You basically get a huge data set, right?
Yeah, so
Okay,
I suppose
thank
hypersync is kind of like the raw blockchain information, and hyperindex is the layer above it, in which you can choose how you want to aggregate your data into your database, and you can... but great question. You can store it as, like how many deposits a user's made, what the total value of the deposits is, and you can get much richer data. At that level, it's a lot kind of easier at hyperindex, but sometimes you might have a custom use case. You need to do something specific, and then you can use hypersync, which is a bit more raw data, but much more flexible.
Thank you.
Cool.
There's an... Yeah.
Thanks for the talk.
Cool.
Is there a way to get access to raw data files? Because you could analyze files on using AWS, Athena, or something
No,
like
absolutely, yeah. So hypersync, we've got 3 clients. So we've got a Python client, we've got a Rust client, we've got a JavaScript client. And if you use those hypersync clients directly, you can import the data you want into Parquet files, and then you can do a whole bunch of cool things. Like we've seen it plugged into ClickHouse, a few other applications. And then you can do your kind of data querying. Yeah. Cool.
Anyone else? We still have a few minutes.
All right.
Okay, then thank you so much, Denham, for your great presentation. And let's wait a few more minutes for the upcoming one.
Cool.
Thanks,
Thanks everyone.